Okay, here I am going to assume we may be having Zoom issues. So I'm going to record the presentation on moments of inertia on the assumption that we may not be able to get online for Zoom. So we're going to calculate the moment of inertia of a solid object. And here, since the mass will be distributed over a region of space uniformly or not, we can calculate the moment of inertia by basically adding up the contributions of each little infinitesimally small piece that is at a certain distance r from the axis of rotation. However, adding up here will now mean integrating rather than literally summing up. So now we have an integral of r squared dm. Notice this is very similar to what we did calculating the center of mass, except it was r dm, and then we divided by the total mass. And the only difference here is we're not going to divide by the total mass, and we're going to square the r. Beyond that, the setup is very similar. So let's consider one example where we have a thin rod that is about one end. And the rod will be very thin, so the thickness right here is very small compared to its overall length. It'll have a length L, a total mass M. The density, we will assume, will be uniform throughout its entire length. So the moment of inertia is the integral of x squared dm, where x is the distance from the axis of rotation. Dm is all of the mass that is at a certain distance x. Well, that'll be this infinitesimally thin little sliver of the rod that is located at distance x from the axis of rotation. Dm, how much mass is there? Well, m over L is the mass per unit length. Multiply that by the thickness, dx, of this little piece, and that's how much mass is there. Notice that is a constant. dm is the same near the axis of rotation as it is far from the axis of rotation, because it's uniform density. So take this, we plug it in there. The limits are from one end 0 to the other end L. So the integral from one end to the other, we add up all the dm's all along the entire length. That then just gives us a calculus problem. M over L are constants, we factor them out. We then need to find the antiderivative of x squared. Well, that's just x cubed over 3. And that's going to be evaluated at the upper and the lower limits. Lower limit is just 0, upper limit is L. Notice one of the L's cancels out, and we end up with 1/3 ml squared. So that is the moment of inertia if I take a rod and I try to spin it around one end. It's only 1/3 ml squared because notice a large quantity of the mass is actually close to the axis of rotation. It's not all at the end. Now, other thing we can do is spin it around the middle. Notice the moment of inertia depends on the axis of rotation. It's not defined for an object. It's defined for an object and the axis we're spinning it around. If we spin it around the middle, everything is the same except for the limits of integration, because we have the same sort of dm and the same formula, x squared dm, and the only difference is now we're going from one end at minus L over 2 to the other end at plus L over 2. The only difference is the limits of integration. Everything is the same except now we're evaluating it at plus and minus L over 2. A little bit of algebra then gives us the 1/12 ml squared. Notice this is smaller because now more of the mass is closer to the axis of rotation, and the furthest the mass is ever from the axis of rotation is half the length, whereas before it was the full length. So this is significantly smaller. It's a 1/12 ml squared rather than 1/3 ml squared. So we'd expect the moment of inertia to be smaller, and it is. Next thing, which is a little more complicated, is to find the moment of inertia of a disk about its center. The disk will again be of uniform density. We'll describe it as a total mass m, radius r, thickness t. Again, we want to evaluate the integral of r squared dm. First thing we need to do is find out what is dm. Well, it's an infinitesimal mass that is all from a distance r from the axis of rotation. Capital R is the total radius of the disk. dm will be something smaller than that. So we need to figure out what is dm. And then we're going to add up all those little dm's basically from the middle of the disk all the way out to the edge. And those will give us the limits of integration. We're going to end up setting up a definite integral, and then we can evaluate it. So we look down from above on the disk, and dm will be all the mass that is at a distance r from the axis of rotation. That will be this little sliver right here, which if I took and cut it out and stretched it out, it would end up looking like a long, thin piece of paper. The length right here is the circumference of that circle, 2 pi r. The thickness of it is the thickness of the disk. And it is infinitesimally thin, so its depth is dr. The amount of mass that we have here is the density of the disk, which is the total mass of the disk divided by its total volume. Its total volume is pi r squared times the thickness t. Remember, t here is thickness, it's not time. And then the volume of this little sliver is basically its length, which is 2 pi r, the circumference of it when it was wound up as a circle, times its thickness, t, times its depth, dr. So now we have a value for dm. It's the total mass divided by the total volume times the volume of this little piece. Limits of integration will just be from 0, the center of the disk, all the way out to the edge. So 0 to the radius r of r squared dm. Then for the dm, we just plug in what we got for dm before, and then we just do some simplification. Total mass is a constant. We can factor that out. There's a factor of 2 right here. That comes out. The pi's cancel out. R squared is a constant. It comes out. I've got an r squared here. I've got an r there. So I have an r cubed dr. And again, the limits are from 0 to r. Antiderivative of r cubed is r to the 4th over 4. We evaluate that, the upper and the lower limits, and we end up with 1/2 mr squared. And that is the moment of inertia of a disk about its center. There's a video on Canvas that also goes through this calculation. It's just someone else doing the same calculation. And I also posted a CDF file, which is the Wolfram Mathematica files that give you more examples on calculating moments of inertia using calculus. Now, I'm not going to prove these theorems. The theorems are stated in the textbook, and they do give a brief proof of them. But the first one I'm going to go over is known as the parallel axis theorem. Parallel axis theorem says, take some bizarre object, and let's say somehow we know its moment of inertia about an axis that goes through its center of mass. So the axis O right here goes through the center of mass of the object, and we'll say we know its moment of inertia about that axis through its center of mass. Then we have a second axis, which is called axis P right here, that is parallel to the first axis. It is not through its center of mass. Then the moment of inertia about P is the moment of inertia about O, which is this one through the center of mass, plus the total mass of the object times the distance between the two axes of rotation squared. I'm not going to prove this, but this turns out to be a very useful formula to calculate a moment of inertia, because typically the center of mass has some symmetries, so often it's easier to calculate the moment of inertia about a center of mass. Then we can calculate its moment of inertia about any other axis, just so long as they're parallel. So consider this example. Here we have a disk right here. We already know its moment of inertia through its center of mass. That's mr squared. Well, what if instead we have it rotate around an axis that goes parallel to the first, but goes through the edge of the axis? Well, here it's just 1/2 mr squared, which is the moment of inertia about the center of mass, plus m times this distance between the two axes squared. Well, that's just r, so it's r squared. So it's 1/2 mr squared plus mr squared, or 3/2 mr squared. Now, we can also calculate the moment of inertia of a thin rod about its center of mass once we've calculated it about one end. So here what we're going to do and this is something in class you would be doing yourself. The moment of inertia about p, which is the 1/3 ml squared, is the moment of inertia about the center of mass, which is what we want to find, plus md squared. Well, the distance between the two axes of rotation is half the length of the rod. So we know the moment of inertia about one end is the moment of inertia about the center of mass plus m times L over 2 quantity squared. Solve that for the moment of inertia about the center of mass, and indeed we get the 1/12 ml squared. So once we've found it about one end, we could use the parallel axis theorem to get it through the center of mass. Or we could calculate through the center of mass and then use the parallel axis theorem to get around one end. Now there's another theorem, and this one I'll tell you is not covered in the textbook, nor is it on the AP exam. But it's another very useful theorem. It's called the perpendicular axis theorem. This, however, only works for very thin objects. So here I have a board right here. It can have an extended direction in both, if you will, x and y, but in the z direction, it has to be very thin. So this only works for thin objects. It then says that the moment of inertia about the x-axis plus the moment of inertia about the y-axis, two axes that are perpendicular to each other, is equal to the moment of inertia about the z-axis. So Iz equals Ix plus Iy. And that can be extremely useful. So, for an example, let's go back to our disks. We know the moment of inertia about, we could call this the z-axis through the center of mass going perpendicular to the surface. Make this to be very thin, and we can then calculate what is the moment of inertia about one going along a diameter. And here I've shown it from the side, and here I've shown it from another side. So this is one where the disk is spinning around like this. Well, here we can calculate the moment of inertia by knowing this is 1/2 mr squared, and then a moment of inertia about this axis, or about one perpendicular to it, will be equal. So we could say Ix equals Iy, and call this one right here z. So we have Iz equals Ix plus Iy. Iz is 1/2 mr squared. Ix must equal Iy because this is a circle, so they're perfectly symmetrical. Spinning around this axis right here, the y-axis, is the same as spinning around the x-axis. So therefore, those two are equal. So Iy equals Ix. So 2Iy equals 1/2 mr squared. Iy equals 1/4 mr squared. So the moment of inertia spinning a disk this way is 1/4 mr squared.